The hill didn't fall all at once. It moved the way ruin always moves, quietly, gradually, then suddenly, all at the same time. By the time the ground fractured open on the southern edge of Sicily on the afternoon of January 25, 2026, the earth had already been in motion for weeks. Roads had cracked, buildings had tilted by centimeters. Subsidence of up to 7 meters had already been recorded by monitoring sensors before most residents had any idea what was coming. And then, on an ordinary Sunday, the kind of Sunday where Sicilian families gather around long tables and the smell of slow-cooked raw food drifts through open windows, the hillside tore itself apart. A 4-kilometer front of land, nearly an entire square kilometer in area, began sliding toward the plain of Gela, 350 million cubic meters of earth. One of the largest recorded landslides in Italian history peeled away from the town's southern flank. Cars were swallowed. Houses that had stood for generations were left dangling over a newly formed cliff edge, their foundations undermined, their walls groaning against the void. One mechanic who watched it happen from his own property said simply, "We watched the landslide happen under our feet. What happened to Sicily was not an accident. It was a conclusion, and understanding why it happened, why it was always going to happen, requires going back much further than January 2026. It requires going back to the geology itself, to the Pliocene, to the very composition of the ground on which this town was built." Part 1. The ground beneath Sicili's southern Sicily is ancient in a way that defies easy comprehension. The rocks beneath its hills record tens of millions of years of geological history. Oceanic sediment compressed into stone, seabeds pushed upward by tectonic collision, marine clay laid down during the Pliocene epoch and never fully consolidated. This is not stable ground in any geological sense. It never has been. The particular geological formation underpinning Sicily and much of the surrounding province of Caltanissetta belongs to a class of material that engineers and geologists refer to as Pliocene clay. These are fine-grained, layered, sedimentary deposits. The kind of material that behaves almost like a solid when dry, but transforms when saturated. Water doesn't simply drain through clay. It accumulates within it. It fills the microscopic spaces between particles, increasing pore pressure, reducing the internal friction that holds the material together. In engineering terms, the shear strength of the slope, its resistance to sliding, drops dramatically the moment those clay layers become waterlogged. This is not an obscure geological curiosity. Pliocene clay formations are among the most landslide-prone geological materials in Europe. Italy's National Research Council has cataloged over 620,000 landslide events across the Italian peninsula, and the regions sitting atop these kinds of clay-rich, Pliocene-age deposits account for a disproportionate share of them. Sicily's interior provinces, Caltanissetta, Agrigento, Enna, sit at the heart of this geological risk zone. Sicily is not an outlier in this landscape. It is one of its most vivid expressions. The town itself occupies a series of rolling hills above the Gela Plain, roughly 15 kilometers inland from the Sicilian coastline. It is a place of roughly 25,000 to 28,000 people, with a history stretching back centuries, layered atop a geology that has always been quietly unstable. The slopes below the southern residential districts descend toward the Mariglio River and the Benefizio stream, drainage channels, that become torrential during heavy rainfall events, and that historically have accelerated the saturation of the clay layers above them. The topography is not just scenic, it is a geological trap. Beneath Sicili's cobbled streets and pastel facades, layers of sand and clay alternate in sequences that absorb water at different rates, creating planes of weakness, what geologists call slip surfaces, where saturated clay meets denser, less permeable substrate below. When rainfall is sufficient and sustained, these planes of weakness become planes of movement. The clay above them literally floats on a film of pressurized water, and gravity does the rest. This is the fundamental physics of what happened in January 2026. But physics alone does not explain why it happened when it did, or at the scale it did. For that, we need to understand what the weeks before the collapse look like. Part 2. Storm Harry and the weeks that built the disaster. It did not begin with one storm. That is one of the most important things to understand about the Sicily landslide. It began with accumulation, weeks of rainfall that progressively saturated the hillside, filling the clay layers, pressurizing the slip surfaces. moving the slope incrementally toward failure even before the first visible cracks appeared. January 2026 was, by any meteorological standard, a brutal month for southern Italy. The Mediterranean had spent the preceding weeks delivering successive waves of heavy rainfall across Sicily, Calabria, and Sardinia. The ground was already above its typical winter saturation threshold when, between January 19th and 21st, Mediterranean Storm Harry made landfall across the central and southern Italian coast. Cyclone Harry, or Storm Harry as it was designated by European meteorological services, brought sustained torrential rainfall in excess of 300 millimeters across a 48-hour window. To put that number in context, 300 millimeters in 2 days is roughly equivalent to 3 months of average winter rainfall concentrated into a single weather event. It also produced 10-meter waves along exposed coastlines. Entire sections of Calabria and Sardinia were inundated. Infrastructure across 3 regions was compromised. But for Nicemi, the most critical effect was not the storm itself. It was what the storm did to ground that was already primed. The clay layers beneath the town's southern hills, already saturated from weeks of preceding rainfall, absorbed the additional load from Storm Harry's precipitation and reached a critical threshold of pore pressure. This is a term worth pausing on. Pore water pressure is the pressure exerted by water trapped within the void spaces of a soil or sediment. As pore pressure rises, it effectively reduces the normal stress holding the soil particles against one another and therefore reduces the slope's resistance to sliding. When pore pressure exceeds a critical threshold, the slope fails. At Nicemi, that threshold was reached not abruptly, but in stages. The first visible signal came on January 16, 2026, when a landslide caused the collapse of Provincial Road 12, the main artery connecting Nicemi to the Geological State Road. The road did not just crack, it disappeared. A section of tarmac and earthen embankment dropped away, severing a critical transport link and serving as an unambiguous warning that the ground beneath was already in motion. The mayor of Nicemi, taking the warning seriously, ordered the evacuation of 35 people from the most immediately affected areas, closed schools, and requested active monitoring from the Civil Protection Department of the Sicilian region. That monitoring would prove critical in the days that followed. Between January 16th and January 24th, sensors tracked a slow but measurable downslope movement of the hillside. The land was not stable. It was creeping, millimeters per hour, accumulating into centimeters per day, moving in the direction of the Marolio River and the Gila Plain below. Civil protection officials documented a subsidence of between 6 and 7 meters across the monitored zone. A landslide front measuring 1 times 6 kilometers was already identified. The situation was serious. What came next was catastrophic. Part 3. Sunday, January 25th. Picture a Sunday morning in the heart of Sicily. The sky hangs low and swollen, clouds dragging heavy curtains of rain across the countryside. Nicemi stirs slowly into the familiar rhythm of its weekly ritual. Families gathering, kitchens warming, the sounds of a town at rest. Below the southern residential districts, men are tending to small holdings, olive groves, and animal pens as they do every week. The landscape looks as it always has looked. Then the cracks appear, not small cracks, not hairline fractures in the tarmac that might be explained away as frost damage or old infrastructure. Wide, jagged separations in the earth, opening along field boundaries, splitting road surfaces, running parallel to the slope's contour lines and the unmistakable geometry of an active landslide front. The men below the town saw them first. Furrows torn open in ground that had been solid the previous day. The sound, witnesses later described, was like nothing familiar, not quite a rumble, not quite a grinding, but something in between, felt as much as heard, coming from beneath the ground rather than across it. Word reached the town quickly. By early afternoon on January 25th, the landslide was widening with visible speed. The Civil Protection Department issued an emergency evacuation order. The mayor declared a red zone across the affected southern districts. 500 people were initially ordered to leave. As the hours passed and the movement continued, that number grew. By the following day, more than 1,500 residents had been evacuated from their homes. What the emergency responders found on the ground was extraordinary. A front approximately 4 kilometers in length had mobilized, spanning the Sante Croce neighborhood, the Belvedere district, and the areas adjacent to the Benefizio stream and the Perillo quarter. The movement was not a sudden avalanche, it was a slow-motion catastrophe. the kind that is, in some ways, more terrifying, precisely because it cannot be outrun by speed, but only by recognition. The land was moving at walking pace, but it was moving. And it was not stopping. The scale of what had occurred became clear from the air. Aerial and satellite images captured in the days following the event showed a newly formed cliff edge cutting through what had been a continuous hillside. Cars sat with their front ends pointing into empty space, their rear wheels still on solid ground. Houses that had stood for decades now balanced on the lip of a precipice, their foundations partially undermined, their walls intact but their ground gone. The Civil Protection Chief, Fabio Siciliano, surveyed the scene and was unambiguous in his assessment. The entire hill is collapsing onto the plain of Gela. According to Italian officials, approximately 350 million cubic meters of earth had mobilized, making the Nesemi event one of the largest recorded landslides in Italy's modern history. The subsidence extended up to 7 meters in the worst affected zones. A safety exclusion zone of 150 meters from the landslide's edge was established, within which access was forbidden even to emergency responders while the slide remained active. By the remarkable grace of the monitoring systems that had been deployed in the preceding days, and by the mayor's decision to act early on January 16th, not a single life was lost. No one died in Nesemi. In a disaster of this scale, that is not a minor footnote. It is the story. Part 4. The historical weight of what had already been known here is what makes the January 2026 collapse not just a geological event, but a human one. Nesemi had been here before. On October 12, 1997, also a Sunday afternoon, a section of the town's hillside had collapsed onto the Gela plain below. 400 people were evacuated. Buildings were destroyed. A church was demolished for safety reasons. The geological cause was identical: saturated Pliocene clay, a mobilized slip surface, a hillside in failure. The disaster of 1997 was not an unknown quantity. It was a precedent, a warning, a document written in collapsed earth and evacuated families that said plainly, this ground will move again. Francesca Aparo was one of the residents caught in both events. Her family home surviving 1997, later demolished for safety reasons, the family relocating to Nesemi's historic center, and then, in 2026, finding themselves once again living adjacent to an active landslide zone facing possible demolition. Her story is not exceptional in Nesemi. It is the town's story. In the weeks following the January 2026 collapse, anger among residents crystallized around a single question: why had so little been done in the 28 years between disasters? Geologists consulted by Italian media in the aftermath were consistent in their assessment. The collapse had been expected. Nesemi's geological conditions were well documented. The town had been included in Italy's national landslide risk inventories. And yet the slope had not been adequately drained, reinforced, or monitored until the crisis was already unfolding. Prosecutors in nearby Gela opened a formal investigation into the disaster. The evacuation had revived what one Associated Press report described as political mudslinging over why construction had been permitted to continue on land that geological surveys had long identified as high risk for landslides. The questions being asked were not only about what happened in January 2026, they were about what had and had not happened in the 28 years before it. Part 5. The climate dimension. The Nesemi landslide did not happen in isolation. It happened within a pattern, and that pattern is becoming harder to ignore. The Mediterranean basin has been identified by climate scientists as one of the regions most acutely exposed to the effects of accelerating climate change. Mediterranean cyclones, the kind of intense, short-duration, high-precipitation weather systems exemplified by Storm Harry, have been increasing in both frequency and severity. The mechanism is well established. Warmer sea surface temperatures provide more energy to developing low-pressure systems. More energetic cyclones produce more intense and concentrated rainfall. More intense rainfall events saturate susceptible landscapes faster and to greater depths. Landslides, particularly in geological settings like Nesemi's, respond to this intensification with predictable severity. Italy has seen this pattern expressed with devastating regularity in recent years. Devastating floods in Emilia-Romagna in 2023, the Ischia landslide of 2022, the Sarno disaster of 1998. Each event has its specific geological and meteorological character, but the underlying dynamic is consistent: a landscape that was already stressed by human development and geological vulnerability, pushed past its threshold by rainfall that is, by historical standards, increasingly extreme. For Storm Harry's arrival at Sicily in January 2026, the numbers speak directly. More than 300 millimeters of rain in 48 hours, 10-meter waves along coastlines, a state of emergency declared for 3 southern regions simultaneously. Sicilian regional officials estimated total damage across the island alone at approximately €2 billion. The Italian government's initial emergency allocation of €100 million was described by officials and analysts alike as a first step, not a solution. Greenpeace Italia, in the aftermath of the Nisemi collapse, issued a pointed statement calling on the Italian government to accelerate its investment in climate change mitigation. The organization argued that systemic inaction on energy transition and climate adaptation was converting routine geological risk into recurrent catastrophe. The Italian government's own civil protection infrastructure, in contrast, was, to its credit, instrumental in preventing the loss of life that so easily could have accompanied an event of this scale. Part 6. The Science of What Remains. The landslide that struck Nisemi on January 25, 2026, was not, in the strict geological sense, over when the immediate emergency response began. It remained active for days afterward. The ground continued to shift. Additional monitoring by the Italian Space Agency was commissioned to supplement ground-based instruments. Satellite imagery collected at 60-centimeter resolution by Worldview Legion on January 27 showed tension cracks and minor scarps continuing to develop beyond the primary failure zone, indicators of ongoing instability. A second image collected on February 2 captured the collapse of an additional building that had been standing precariously just 1 week earlier. The nature of these clay-based landslides makes stabilization genuinely complex. Unlike rock slope failures, which can sometimes be reinforced with anchor bolts and retaining walls, deep-seated translational slides in saturated clay require, above all, drainage. The poor water pressure that drove the failure must be reduced. Drainage galleries, horizontal drains, surface water management infrastructure. These are the engineering tools that can, over years, begin to stabilize a slope that has been mobilized, but they require sustained investment, long-term monitoring, and political will. Civil Protection Chief Fabio Siciliano was direct about what the affected residents should expect. The homes on the landslide's edge could not be re-inhabited. Permanent relocation would be necessary for families whose properties now sat in geologically active terrain. The question of where those families would go and who would pay was, in late January 2026, still unanswered. What satellite analysis did confirm was the scale of the vegetation and soil disturbance. NVI analysis, a measure of vegetation health derived from near-infrared satellite band data, showed the full extent of the area stripped of its surface layer, the boundary between what had moved and what had remained, and the early indicators of where further movement might still be possible. Emergency responders were using this data not only to assess what had already happened, but to predict where the next failure surfaces might emerge. Part 7. What Nisemi tells us there is a temptation, when confronted with a disaster like Nisemi, to reach for the language of the exceptional, to describe what happened as unprecedented, unforeseeable, a once-in-a-generation event. The geology of southern Sicily does not permit that comfort. Neither does the historical record. Neither does the direction in which the climate is moving. What Nisemi tells us is, in fact, something much more unsettling than the exceptional. It tells us about the ordinary, about the accumulation of ordinary decisions. To build on unstable ground, to defer remediation, to underinvest in drainage and monitoring, to treat geological risk as a problem for the future. The conditions for the January 2026 failure were written into the landscape long before Storm Harry arrived. They were written in the Pliocene clay formations. They were confirmed by the 1997 landslide. They were reinforced by 28 years of insufficient mitigation. Storm Harry was not the cause. It was the final increment of load on a slope that had long since exhausted its margin of safety. Italy is not alone in this. Across southern Europe, across the Mediterranean basin, across every landscape where the combination of weak geology, steep topography, dense human settlement, and intensifying rainfall exists, versions of Nisemi are waiting. Some will fail with warning like Nisemi because monitoring systems and decisive local officials act in time. Some will not. The residents of Nisemi are, as of early 2026, dispersed. Most have stayed with family. A small number were housed in a temporary reception facility at the Pio La Torre Sports Hall. Their futures are uncertain on the specific way that only those who have watched their neighborhood dissolve into a cliff edge can understand. Francesco Zarba, one of the evacuated residents, put the situation with the plain directness of someone who has run out of patience for systemic failures. We had the first landslide 30 years ago, and no one ever did anything. The hill is still moving, slowly by most measures, but moving. And beneath the remaining streets of Nisemi, beneath the pastel facades and the cobbled squares, beneath the neighborhoods that have not yet been evacuated, the clay layers are still saturated. The pore pressures are still elevated. The slip surfaces are still present. The geology that made this disaster inevitable is not going anywhere. It is the same geology it has always been. The question is not whether the ground will move again. The question is whether, this time, something will be done about it before it does.